three famous laws of motion. And the idea is, remember we were talking about how Aristotle said that objects that are twice as heavy should fall twice as fast. You could say that would be a law of motion for Aristotle, except he was totally wrong, right? So the idea is somebody had to make up some laws that were accurate. And we've already talked about Galileo, and indeed the first of Newton's laws basically is based on Galileo. So we're going to talk about Newton's first law of motion, Newton's second law of motion, how forces and about forces and interactions, Newton's third law of motion, and the summary of Newton's third law. Sorry, that's what it says. Okay, now, did we already cover the first law? No, we didn't get very far. Okay, so I'm sorry, I've got my physics classes also had lectures on this. Okay, so sometimes I get a little confused about where I am. It's almost exactly the same book. It's the same author, so it uses that. So it gets a little confusing sometimes. Now, Isaac Newton lived from 1642 to 1727, and you may remember the date 1642, though you probably don't. Anybody remember what happened in 1642 that we already discussed? Probably not. It's the year Galileo died. So the interesting thing there, Newton was born as Galileo was dying. But Galileo had lived a very long life. And so the worlds that they entered were a little bit different. Things were a little freer religiously in Newton's time. The Reformation was well underway. And so he wasn't, and he lived in England instead of Italy. So he didn't have as many problems with trying to come up with his ideas, that there was opposition to them from the church. Anyway, so Newton was an English scientist, a mathematician. He was only 25 when he made a lot of his discoveries. And there's a reason for that. Well, sort of a reason, besides the fact that he was brilliant. He had been a person who probably shouldn't perhaps have been a scientist. His dad was a farmer, and so he would usually grow up to be a farmer too, perhaps. But what happened was that his father died when he was actually before he was born. His mom remarried, and evidently the new dad didn't really want him, so he was dumped on his grandparents and lived with his grandparents. And so he never came to inherit that family farm, really. I guess the new dad took the farm. But anyway, what he did was they started training him to be a farmer, and he was found to be sort of hopeless. And an uncle said, no, this kid is really smart. Let's send him to college. And so they sent him off to, I think it was Cambridge. And so he was happily doing pretty well at Cambridge. And then what happened was the plague struck. So rather like now, the colleges closed down, but since there was no Zoom or anything, the students just had to go back to their homes and stay there. So they were sent back to the countryside, especially to get them out of the cities. And so there he was, stuck at his grandparents. And so he started working on his ideas. And so anyway, you can see where that pandemic was drove Newton back out of his social life, out of school. And what he did at home was, instead of watching YouTube videos, more like my son, he was in there developing ideas. See, no YouTube either. So imagine being stuck at home. Okay, so anyway, so along the way, he invented calculus. He invented the reflecting telescope, which is what really made him famous amongst scientists, because telescopes that use lenses like Galileo's, the problem is that different colors of light go in different directions. So if you're looking at the sun, for instance, well, that's not too bad because it's so big. But you look at stars and things, and it's a little bit fuzzy because the different colors from the light are going in different directions. So anyway, the reflection telescope uses mirrors, and so that worked better. And so that was actually something that everybody really admired, and they brought it to the attention of the king. And so that's how Newton first started getting famous. Now I put the cat door in here just because I think it's kind of funny. He's supposedly the first person recorded in history who made a separate door for cats. So anyway, he liked cats. Okay, he did research in motion, and so like Galileo and Aristotle, except he did research, unlike Aristotle. He studied light, so he took light and broke it into its colors with prisms and then put it back together. He also, of course, is the person who came up with the law of gravity, which is a chapter we're going to skip over. So it's chapter 4. Unfortunately, we're going to skip that. But yes, that was pretty profound too. And so the idea of the apple dropping and him coming up with ideas about gravity, that was Newton too. He developed 3 laws of motion and the law of gravity. He wrote books. So his Principia, Mathematical Principles of Natural Philosophy, is very famous, laid down these laws. And then he wrote another one on optics, which was the basis for physics in the 1700s. Okay, so let's look at the first law of motion. It's going to look familiar. The first law of motion says every object continues in a state of rest, so at rest, or of uniform speed in a straight line, unless acted on by a non-zero net force. And I forgot to get the tablecloth thing set up. Maybe I can get it set up during break. The problem is I've got my table covered with rocks now too, because I'm teaching geology, so there's a lot of rocks over here. Anyway, so anyway, here's a big rock, and either it's not moving or it's waiting for a force to move it. And so that's the idea, right? Objects will either stay at rest or uniform speed in a straight line. So what does that sound like? We've got equilibrium sort of thing here, right? Resting is equilibrium. Uniform speed in a straight line is dynamic equilibrium and static equilibrium. So these objects have a non-zero net force. Okay, so he was really talking about these 2 states of motion we were talking about earlier, static and dynamic equilibrium. Okay, so inertia is something, the idea that Galileo came up with that we talked about, the tendency of an object to remain at rest or in uniform motion in a straight line, and to resist changing their motion. So when you want to change the motion of an object that has inertia, then it requires a force. So Newton is the one who went off and decided that, yeah, inertia relates to mass. So greater mass, greater inertia. Okay, so mass and inertia. So if you say something is 10 kilograms of mass, you're saying it has 10 kilograms of inertia in some ways. So here you've got a little kid and a big guy, grandpa, on the swing. And the idea is that it's easy to make the little kid move, right? To change its motion. You can start it moving easily, and you can grab the swing and bring the kid to a stop. But once you get the big guy going, it takes a lot more force, right? And then once he's moving, you don't want to get in front of him because it's going to take a lot to stop him too, a lot of force. And so, yeah, so inertia, he has more inertia than the kid. And so he will take more force to stop it. Okay, so this is a mini tablecloth trick, and if you've never done this yourself, it's actually kind of interesting to do because you're like, oh yeah, but when you actually do it, it's very impressive. So make a stack of quarters, pull a piece of paper out from under the quarters, and it's kind of stunning how they just bloop, stay there. You expect them to fall down and scatter, and they don't. So try it yourself, as Galileo would say. Oh, and the discussion question, getting some good answers in there. So I read all the answers. Let's see, Saturday. Anyway, we're getting some good stuff in there. So keep that up. Looks like you guys are all believers in Galileo. So. Okay. So as he would say, try it yourself. Okay, so a spacecraft keeps going because there are no forces acting to stop it. So spacecraft keep going, right? So they can go out into space. We talked about that. We've got spacecraft that are moving for around 50 years, and they're still going. Okay, now if you're driving along and you suddenly have to put on the brakes, you feel like you're being thrown forward. And of course, that's not what's happening. What's happening is that you already had motion. You were moving at a constant speed in the car. And so it takes a force to stop you. So if you don't have a seatbelt on, then you're not tied to the car, which has brakes. And instead, you're going to continue with your original velocity. And so you're not being thrown forward, but you are continuing to move forward. And so that's very dangerous, which is why we wear seatbelts. I'm someone who's met up with a hard surface with my head when I was in a car wreck when I was a kid, and the car did not have seatbelts in the back seat, if you can believe it. Cars used to be manufactured without seatbelts in the back, and well, they used to be manufactured without any seatbelts at all. But yeah, you are going to keep moving forward till you get stopped by a force. And so anyway, so you always want to wear seatbelts. People who think they're going to be thrown clear of a car wreck are just delusional. Yeah, you might get thrown clear, but how do you squeeze out of a window without ripping your arm off or something? And then hitting the ground at 30 miles or 60 miles an hour? Not good. So yeah, you want to stay strapped to the car. So when the car stops, you stop. Okay, so anyway, yeah, and then the car rolls over on you too. That's usually bad. Okay, so wear those seatbelts. Okay, now you've got some homework problems on this in your chapter 2 homework and your chapter 1 homework, I think. The idea of inertia in, say, an airplane. So the idea is that when you get on an airplane and you've got a coin in your pocket and the plane starts to go until it's going at 500 miles per hour, well, so is that coin. So you're going at 500 miles per hour. The coin is going 500 miles per hour. And so what happens is that when you take the coin out of your pocket and throw it up in the air, it doesn't fall to the back of the plane because it's still going 500 miles per hour in the direction of the airplane. Okay, so it should just stay with you and be able to come back to your hand. So the thing is, though, what would happen if the plane sped up? So all of a sudden you start to go faster. Then what happens is if the coin is in the air, then that coin could fall behind. So it might fall behind your seat or hit you in the top of the head. And the other thing that could happen is that maybe you slow down. Okay, so the plane slows down. And in that case, the coin is going faster, so it might fall in front of you. Okay, so the idea is that the coin has the speed of the airplane, but when it's in the air, it's not receiving any forces to speed up or slow down, whereas the passenger strapped in his seat is getting those messages. And so one of the reasons people didn't want to believe in a moving Earth was because they worried about the idea that if the Earth was moving, then yes, animals, who were in the air, objects that were falling through the air would get left behind. And so like this bird, if it starts to fly out into the air, then it isn't traveling with the Earth anymore, they thought. But once Galileo explained the idea of inertia, then people could see that this bat bird thing um, is already moving with the same speed as the Earth, even though the Earth is going 67,000 miles per hour. And therefore, it will keep up with the tree and the Earth and be able to catch its worm. So any motion that we make on the Earth is on top of the motion we already have from the Earth. So you're moving at 67,000 miles per hour right now. And so if you jog to the store or something later, then what happens is that you will just add that motion onto the 67,000 miles per hour that you've been moving your whole life. You've been moving that fast. Okay, so forces are pushes or pulls, and they are vectors. Remember, vectors have a direction. Okay, so vectors have a direction and they can produce a change in motion. So forces cause changes in motion. So things can speed up, things can slow down, things can change their direction. Okay, so you can change the velocity, right? So we talked about that. Speeding up, slowing down, changing direction would change velocity. And that's called an acceleration. So remember, acceleration is the change in the velocity divided by the time. Remember, delta means change in, right? So delta V. Now, forces do add up. Forces can subtract from each other if they're in opposite directions. So forces can cancel. And so if you have a force on an object, it may not produce a change in the motion because other forces may balance it or cancel it out. So when I push on one hand, right, then I'm changing the motion. But I can oppose the motion too, right? So my hands can move or stay where they are because I'm pushing on each other. Okay. So anyway, so yeah, so there's a net force that you have to think about. And so it's only a net force that actually causes a change in the motion. So we've talked about how forces can add, right? So here I've got 5 newtons of force plus 5 newtons of force, and it can add to 10 newtons, right? And so forces can add or subtract. So if the forces are balanced, then you wouldn't expect any change in motion. And unbalanced forces result in a change in motion. And by the way, who's going to win? Often it depends on who has the best shoes. Um, so if one team often is able to dig their feet into the ground better, they use that force, which we're going to talk about Newton's second law soon, and his third law, that relates to tug of wars. And if you've never done a tug of war, sometimes ECC has a tug of war in the spring usually. So that would be this term. And they have a party thing, and students can participate in a giant tug of war. And so unfortunately, it looks like we're missing out on that this year. Once my students, I brought classes of students down and they joined in and we had a team Galileo and a team Newton pulling to see who would win. Okay, so Newton's second law of motion is called the law of acceleration. So each law has its own little nickname. So the first law was the law of inertia. The second law is the acceleration law. Sometimes I also call it the equation law because it does have an equation linked to it that sometimes students forget. Okay, so So anyway, so the acceleration on an object is directly proportional to the net force. It's inversely proportional to the mass. Now, what do we mean by directly proportional and inversely proportional? When we say directly proportional, we're saying that when you increase the force, the acceleration also increases. So they both go up together. Inversely proportional is if I increase the mass, then the acceleration goes down. So they go in opposite directions. Okay, so directly proportional together, they move. Inversely proportional, one goes up while the other one goes down. And so over here in the illustration, you've got one hand pushing on a brick. That produces a certain acceleration. And then you've got twice as much force, two hands, so that would produce twice as much acceleration. However, if you've got twice as much mass, well, the problem with twice as much mass is that starts to reduce the acceleration, and it reduces it back to its original value. Okay, and a formula way of looking at that is this formula. Acceleration is the net force divided by the mass. And we're going to go look at that on the next page. So, okay, so acceleration is the net force divided by the mass. And so we often are going to use the equation this way. This is the way Newton used it a lot. And so let's say that you were pushing on the brick and you were using 10 newtons of force, and the brick was 5 kilograms. Okay, so what's that going to give you is the number 2, and the unit is going to be acceleration. So meters per second, or meters per second squared. Okay, and so often we don't necessarily put the N on the force, because in physics it would be written with a bold or an arrow over it, and it would mean net force. But remember that the equation is always referring to the net force. So there should, I don't know why it's not drawing for me. Oh, that's why. Okay, so anyway, come on, draw. Oh, now it's drawing. Okay, so this will always be net force divided by mass. And often you'll see this equation written in different ways. So turn it around and it becomes F equals ma. And again, that should be the net force. And so that's the way you'll often see this equation written, is F equals ma, but usually people leave off the net. So, as a physics student, you should know that it's there. So net forces produce a change in motion. And so one of those things is that, yeah, you've got to think about the forces on an object. I mean, you can push on the wall all day long, but pushing on a wall isn't going to make it move, because usually, unless you're the Hulk, because there's a force from the nails and whatever's binding it to the ground, the frame of the house, that is pushing back. So you push on a wall and you're not actually moving it. So you have to think about the net force, not just one of the forces, which may be the one you're applying. Okay, so okay, another thing that's in this chapter is free fall. So free fall is when the only force on an object is gravity. So we're saying no air friction or negligible air friction, so very small amounts of air friction. And so then the object is just accelerating with the acceleration of gravity. And in that case, it accelerates at an acceleration of 10 meters per second, or 10 meters per second squared. So as we were talking about, for falling objects, the acceleration is 10 meters per second per second. So acceleration, and remember we call that g, okay? And we use 10 meters per second squared in this class, even though we know it's really 9.8 in a harder physics class. Okay, but remember Galileo said all objects fall at the same rate, the same acceleration, as long as friction was, you could ignore it. And so what's going on there? Well, twice the force on twice the mass. You remember Galileo, one brick, two bricks tied together. And that would produce the same acceleration. But why? You've got more force. So shouldn't something accelerate more if it has more force? Okay, so what's going on there is that we're using Newton's law here to find the acceleration. The acceleration is the force divided by the mass. But what's the force? Well, the force on this is mg, the weight. That's the weight of the object pulling downwards. That's the force. The weight is mg. And then we're dividing by the mass, so that just gives us g again. So the masses cancel out, and we're left with g. Now, if we're having two bricks tied together, then what happens is it's twice the weight, because each brick is mg in force. And so now we've got 2 mg divided by twice the mass, though. It's got inertia. So there's twice as much inertia, twice as much resistance to changing the motion. So what happens is that those cancel out, and you're just left with g again. Okay, so that's why the objects fall with the same rate, the same acceleration, if you don't have to put air friction in there. So because you might have more force, but you also have more inertia. And so one speeds things up, the other one slows things down, resists changing the motion. Okay, so all objects fall at g. The greater the mass, the greater the force, but also greater inertia. And that gives the same value. So just what I was saying a minute ago. Oh. Okay. Just a minute. Okay, all right. And you can relate this to the idea of pi. When the Greeks discovered pi, is because they were doing ratios of circumference divided by diameter. And a big circle and a small circle each had the same value of pi for that ratio. And so the same thing for a rock and a feather, force divided by mass keeps coming back to be g every time. Okay, now I was just putting in some stuff about weight, which we haven't actually done yet. So here it is. Weight, your weight is m times g. And so it's mass times acceleration due to gravity. And so weight, for this book, we use m times 10. So on this earth. Okay, so here's a little dog, 6.2 kilograms. So usually the ratio of pounds to kilograms is around 2.2. So this dog is only about 12 to 15 pounds. Okay, he's a little guy. And so anyway, so just double the mass, and that will sort of give you an estimate of the weight in pounds. Okay, but to find the actual weight in newtons, then we're just going to multiply by 10. So 6.2 times 10 is 62, and that comes out as kilograms times meters per second squared. And so that unit is called a Newton, so the unit of force. So kilograms meters per second square becomes newtons. So 62 newtons is the weight or force of gravity on this little dog. Okay, now objects falling fall at the same rate. Did we already watch the moon feather hammer drop? Yeah, okay, good, thank you. Okay, again, 2 classes. Sometimes it's hard to remember. Okay, so we already found out that yes, that on the moon things are falling at the same rate, and so that worked. Okay. Now, having talked about free fall, there's also non-free fall. What happens if you do have to think about air resistance or air friction? So air resistance becomes a second force. So you have the force of the weight pulling the person downward, and that weight is always going to be mg. And then you've got the air resistance pulling upwards. And so in this book, they're going to give you an R for air resistance or air friction. And both of those will be newtons of force. Okay, so weight is always mg. Air resistance is going to be R. And so when we look at a person who's falling, you can play around with that to figure out their acceleration. So acceleration is going to be the net force divided by the mass. And the net force is the weight minus the air resistance, or W minus R. So we end up with a formula that has W minus R divided by the mass. And since we know that the weight is mg, then we can come up with this formula. Okay, so, all right. Now, I don't always use this formula because I like to calculate the force of the weight first separately. Okay, so anyway, but this can be a handy formula. And so we're going to go and figure out what's happening with someone who is falling. Okay, so all right. Okay, so let's take that formula or that idea. Let me get some color that's not red. Okay, so we've got someone who is falling, and let's not give them a parachute right now, although it doesn't matter. Okay, so they're falling out of an airplane. They've got their parachute on their back. Okay, and the thing is that as they fall, then there is mg, their weight, pulling downwards, and there's going to be some air friction, R, pulling the other direction. Okay, so to find the acceleration, we just need to take that weight minus the air resistance and divide by the mass. Okay, so let's give this person a mass. Let's say that this person has a mass of 60 kilograms. Okay, then that means that the weight, see, I like to usually figure that out, put it on my diagram. So the weight is going to be mg, so that's going to be 60 kilograms times 10 meters per second squared. So it's going to come out to 600 newtons of force. And my air resistance, let's start out with an air resistance of 120 newtons. Okay, so they're falling, and so their weight is 600 newtons minus their air resistance, 120. And we're going to divide by the mass, which is 60. So when you do these problems, okay, so you've got some homework problems on this, and there will be some on the test like this too. Don't forget to make sure and get your weight, okay? You don't want to use 60 for the weight because that's not what 60 is. 60 is the mass, not the weight, okay? So make sure you know the difference between mass and weight. Okay, so now we've got this. Okay, so 600 minus 120 is going to be 480 newtons. And then I'm going to divide by the 60 kilograms. And so 480 divided by 60 is going to be 8, right? 6 times 8 is 48. So cancel out the zeros, and I just get 8 meters per second squared. Okay, so newtons divided by kilograms should give you back the acceleration units. Okay, so I've got acceleration. Okay, now the thing is, let me shift to the next page for a minute. What happens is air friction is proportional to the surface area. So like the difference between having a parachute and not having a parachute. It's also proportional to the speed. So this person is falling, and they're falling, and so they're getting faster, right? Because they are accelerating. Every second, they're gaining 8 meters per second of speed. So they're falling and they're getting faster and faster. So what happens is that their air resistance gets larger and larger. So let's say their air resistance gets to be as high as 300 newtons. Okay, so how is that going to change things? So that's going to change just this part, just the air resistance, right? You still have the same weight, and you still have the same mass. Okay, so then that's going to change this. Now this becomes 300. 600 minus 300 is 300. Now I've got 300 over 60. So now it's going to come out to be 5 meters per second squared. So the acceleration is less, but they're still accelerating, still speeding up. So since they're going faster and faster and faster, then that means that the air friction is going to keep getting greater. Okay, so the air friction gets greater as they fall. Okay, so now let's say that the air friction is so great that it starts to equal the weight. So the air friction gets up to 600 newtons. Okay, so how's that going to change things? Well, now we've got 600 newtons, which means that 600 minus 600 is 0. And what's 0 divided by 60? Well, anything time you 0 divided by anything is just 0. Okay, so what's happening? When the air friction amount reaches the same as the weight, well, all of a sudden there's no more acceleration. But the person is traveling really fast. They're just not accelerating. Now they're moving at a constant speed. Okay, so air friction builds up and builds up and builds up, and then it builds up to be as much as the weight. Now, it's not going to get greater than the weight, usually, if nothing else changes, because it's not accelerating. It's not changing its speed. So it's not going to have its air friction change unless you pull the parachute. You pull the parachute, Suddenly, you've got lots and lots of air friction. And so because of that, your air friction all of a sudden might be greater than the weight. So there you were falling at a constant speed, but you pull your parachute, and all of a sudden, now your air friction goes up to, let's see, 1200. Okay, suddenly you've got a lot of air friction. So what's going to happen? Well, put in all that air friction, and all of a sudden what you've got is 600 minus 1200 is 600. And so your net force is 600. And so divide by 60, and now you've got, and of course, that's going to be a negative, right? Negative 10 meters per second squared. And remember, negative means other direction. So if we were saying this person moving downward was positive, which we haven't put in anywhere else to say otherwise, the negative sign there means that the person is going to slow down, a negative acceleration. They're going to start slowing down. And so that's what happens, right? You pull your parachute, you start to slow down. And so you can get slow enough to land safely. Okay, so air friction can change. And it can change just because you're going faster or slower. It can change because you pull your parachute out and change your surface area. Okay, so air friction is proportional to surface area and speed. So if you change either of those things, then you change the air resistance or air friction. Now, there was that, we were just talking about what would happen, one of those cases where the acceleration reached zero. And so what happens is that air friction increases till it equals the weight. Once it equals the weight, the net force was zero. There's no more acceleration. And it has reached a certain speed. So someone falling reaches a certain speed and stays at that speed. And that's called their terminal velocity. So when you reach terminal velocity, so most things do when they fall through the air, if they fall long enough, they reach a terminal velocity. And that doesn't mean you're the one you're going to die at, hopefully, but it just means the last or highest speed that you reach. And so they start falling with a constant velocity with no acceleration. And this is what would happen with skydivers before they pull their parachute. They would reach terminal velocity. Now, terminal velocity happens when the force of friction equals the weight. And so here are just some typical examples. So remember to figure this out in miles per hour. You just have to double it. Okay, so 145 miles per hour for 145 meters per second would be around 300 miles per hour. That's how fast a shot, okay, so a cannonball, a bowling ball that you let fall out of a plane. You would never want to do that, right? It's going to go very, very fast. Okay, a skydiver is usually going around 120 miles per hour. And this is before they pull their parachute. And if you drop a basketball, it's only going to go around 20. It's got a pretty big surface area, not that much mass, right? So it's only going to end up around 40 miles per hour. Raindrops, when they fall, they reach their terminal velocity really fast. And so within a second or so, they usually are at their final speed. And that is only going to be about 14 miles per hour. And that's a good thing, because if raindrops fell without a terminal velocity and they kept accelerating and accelerating, then they might hit you with like, going 1,000 miles per hour. So we don't want that. So we're fine with raindrops reaching a terminal velocity. Um, and now when a parachutist pulls their parachute, then often they end up going only about 10 miles per hour. And so once you pull your parachute, then what happens is that you're slowing down. Eventually, remember, as you slow down, your terminal velocity, I'm sorry, let's see, your air friction gets less because air friction depends on speed. And so your air friction gets less, and then eventually it reaches your weight again. And so you end up back at a, a slow speed, okay, back at moving at a constant speed, but much slower. So before you were up here, now you're down here. They're both terminal velocities, but once you pull your parachute, you've got that big surface area. So it's a lower terminal velocity. And people always want to know about pennies. So if you drop a penny off the Empire State Building or the Sears Tower, or the Willis Tower, or whatever it's called now. Anyway, if you dropped a penny off, which you usually aren't allowed to do, it would eventually go around 35 meters per second, which would be about 70 miles per hour. So is that going to kill you? Well, Mythbusters tried this, and they found when they were shooting pennies at 70 miles per hour at each other's hands and things, that it would indent and cause a little bit of bleeding. So it would make cuts in the hand, but otherwise you were pretty safe from pennies. So unless you are looking up and you're saying, oh, look, there's a penny and it goes right into your eye, you're probably pretty safe. Okay, so it's not going to make a big dent in your head even. Okay. Um, Okay, so does weight make a difference in terminal velocity? That's one of your homework questions. And the answer is yes. Here we have two people falling. And let's say that one is twice the weight of the other, although that's a big difference for humans. But let's say that this person is only 50 kilograms and this person is 100 kilograms in mass. Okay, the thing is that what happens is as they start to fall, remember that from the very beginning, the larger person has a weight of mg, which would be 10 times 100, okay, or 100 kilograms times 10. So that's going to make 1,000 newtons of force. Whereas the other person, mg is just going to be 500, 50 times 10. So twice as much force pulling down on them, which means that when you come to the net force, okay, so the acceleration is going to be the weight minus the air resistance divided by the mass. And the thing is, their air resistance may be similar somewhat because their surface area is similar. And so what happens is that from the beginning, the weight of the larger person is going to make a larger acceleration, right? Because the net force is going to be greater. And so because of that, then this person will be accelerating faster. So it's going to pass the other person by. Now, as it goes at greater speed, because it's accelerating, then it will start to build up more air friction. But it will, because it has so much more weight, it'll take longer for it to reach its terminal velocity. So smaller objects, lighter objects usually reach their terminal velocity pretty fast. So this person will reach their terminal velocity first because the air resistance just has to be 500. The other person will only reach the terminal velocity when the air friction becomes 1,000. So they have to be going much faster for that to happen. So their terminal velocity is going to be greater. And so you might have the smaller person, maybe with a terminal velocity of, let's say they're going 5 meters per second with a parachute. But the other person, their terminal velocity might be higher, 8 meters per second or something. Okay, so they're going to go faster, so they're going to reach the ground first. And so they won't have as long in the air if they are a larger person. So definitely weight does make a difference for terminal velocity. Okay, it's about time for a break. Let's see. When we're going to look at a review sheet. No, not a review sheet, a worksheet. So let's go to here. Okay, and if we go to the weekly course module and back in chapter 2, okay, so there's a worksheet here we're going to look at, okay, and that will be extra credit, okay, but we're going to look at that today. So if you want to drag out this worksheet and print it off or just have it ready to go, we're going to look at that after the break. Okay, so let's take a break. And so get that worksheet up. Okay.
Thank you.
Okay, sir.